today it's about filters, and tomorrow, for the last seminar of the day, it's going to be about DAC design. And the one about DAC design, that was a bit problematical because I've been thinking about doing this kind of thing for some time. And over the last 2 months, I got in my mind what I was going to talk about in terms of DACs. And I'm busy writing presentations for the DAC design. And then I suddenly realized, hang on, I've only got an hour to do this thing. And I'm already at 25 slides, and an hour is normally 25 slides, and I haven't even done half of what I want to talk about. Fortunately, this particular presentation is a little bit faster, and everything was right. I didn't need to cut anything out. So what I'm talking about is the importance of timing and filters, and how the interpolation filter inside a DAC reconstructs the timing. Firstly, though, I'm going to talk about sound perception. When you look at visual processing, only 10% of what we actually see comes from the eyes. The other 90% is the brain doing visual processing. And science understands quite a bit about how one would actually create a machine to do visual processing. Because, of course, we've got robot cameras that can pick things up, do all this kind of thing. And it's fairly easy to work out how you would create a program to delineate objects and separate objects out into physical entities. We know something about the way the visual system works. This is also true about sound perception. What we hear is not the output from the ears, but the brain processing and interpreting what we're hearing. So the brain separates sounds out. It also locates sound in space and puts a placement tag onto that separated sound. The whole audio scene that we normally perceive is something that's completely created inside the brain. And this processing, we have absolutely no idea how the brain manages to do that. No idea. And imagine the difficulty we have when we're trying to use a computer, and a computer recognizing your voice. But a computer couldn't handle half a dozen people in a party talking at the same time. But you can, because you can hear things and you separate those individual sounds out. And there's some very complex processing going on. So here's a little example. Banjo, guitar in a pub, and some singers. And you hear this, you locate the instruments in space very, very accurately. I was at a thing with my son who plays the guitar. He was doing a little thing at a concert. The hall was about 50 feet deep. And there was a pianist, a violinist, and a trombone player. And they were separated by about 3 feet, like going backwards. Shutting your eyes, you can clearly hear that delineation in depth. The depth placement accuracy the brain has got is extraordinary. And of course, each instrument has its own timbre. Now, the problem we've got for high-end audio is that we do not understand how the brain does this kind of processing. And generally speaking, when you're designing stuff, the traditional approach is to take the performance of the ear into account. So it's about the psychoacoustic performances of the ear. And the normal assumption is that if something is smaller than the perceptual thresholds of hearing, then we can ignore it. And I suppose that's not a bad idea. If something is smaller than that the ear can detect, why worry about it? The problem is, I've often heard errors that are well below the threshold of audibility. Some errors at minus 140, minus 150 dB. There's no way you would hear that error on its own. The ear can't detect that. But the brain processes the information from the ear, and those very, very small errors interfere with the ability of the brain to process that information. So we can't make assumptions about how hearing works because we do not understand how the brain functions. My approach about this kind of thing is that whenever I detect an error, measure an error, or simulate an error, then I have to do listening tests to determine whether that particular error is audible, and then that particular variable, reduce it until I can no longer hear the difference. And there's been some very surprising things that have happened when I adopted that approach. Audio chips are always designed by measured performance. I've had a career, excuse me a moment, designing chips as well as designing high-end audio. And I've dealt with very clever engineers and they never talk about sound quality because it's not something that's part of their parameters of operating. It's just about the measured performance. So, what do we know about perception in terms of timing and location? We do know that there is something called the interaural delay. Now, these are a set of neurons that are connected from the left ear to the right ear. And these neurons fire when it receives a simultaneous signal from the left ear and the right ear. The neuron delay is about 4 microseconds. And this delay is used to determine where sounds are located in space from left to right. It's part of the ability of the brain to detect where instruments are located. So we know this is a fact, and we've done it from various different experiments. Like in the 1950s, they had conscious cats, and they opened up their brains and managed to detect these neurons and fired signals into their ears, and they could see the neurons firing. For humans, of course, we can do it by simple phase shifts and saying, can you hear the change in terms of phase shift? And from that, we can do the discrimination. It calculates the placement to within 2 degrees, and it also calculates depth perception to extraordinary levels of accuracy. Depth perception is done with lots of different cues. Some of it is bandwidth related, something is further away, there's the natural attenuation of the air, and that is used as part of the cue. Part of it is the reverberant fields and the reverberant information, very, very small details that give you a sensation of depth. Now, the interesting thing about the 4 microseconds threshold, which we know about with certainty, is that implies that the brain is processing at a 250 kilohertz sampling rate, which is much, much bigger than CD. Transients and bass. They've done some experiments where they've had a bass guitar. Now, the ear is quite poor at bass. When you look at the analysis of the bass of the ear's performance, frequency response is awful. It's got a lot of distortion. And the ear has difficulties recognizing pitch of low frequency components. The only way you can follow the tune of a bass guitar is actually from the initial transient. And they've done experiments where they've removed the initial transient of a bass guitar, and then you cannot tell what that frequency is actually happening. So you can't follow the pitch at all. It's just a low frequency lump of noise. So transients is very, very important for bass perception in terms of pitch. Transients and timbre. Timbre also depends upon transients. If you remove the transient information of a trumpet or a piano, it becomes virtually impossible to tell the difference, surprisingly, between these 2 different instruments. So why is digital audio so bad? Part of the problem is the timing of transients. Because as I've talked about before, we perceive pitch from transients, we perceive soundstage from transients, timbre from transients, and the starting and stopping of notes, obviously, from transients. The problem that digital audio has got is that people are constantly thinking about simple frequency response. And of course, we cannot hear above 20 kilohertz. I can't hear above 15 kilohertz. And so engineers have thought about CD in terms of just simple frequency response. They haven't worried about the issue of the timing of transients. And with the timing of transients, this is as I've just discussed, this is a major problem in terms of perception of music. Very small timing errors in terms of the reconstruction of transients has quite a profound effect. When I first started theorizing and working out about this, when CD first became available in 1984, my point of view was that we needed to reconstruct transients to an accuracy of about 4 microseconds. I actually was wrong about that. We need to reconstruct transients to an accuracy of the order of 100 nanoseconds or less. It's actually a very big and profound problem. Now, the original timing that was inside the continuous analog signal that's in the A to D converter, that is reconstructed by the DAC's interpolation filter. And the problem is that conventional DACs do a poor job at reconstructing the original analog signal that was inside the A to D converter. And that's what a DAC is supposed to do. It's not about reproducing digital data. You often see people talking about bit-perfect data and all this kind of thing. It's not what a DAC is supposed to do. The DAC is not reproducing data, it's trying to reproduce the analog signal that was in the A to D converter. And that's a very different emphasis on what's going on. So I've got a very simple illustration of the timing problem. And we've got a 20 kilohertz sine wave burst here. And if you sample this burst at this point here and then this point here, you get this digital data. If we then put this digital data into a minimum phase or an IR filter, in other words, any filter that's got no pre-ringing, you end up with this output. And this is actually 100 microseconds worth of timing error. And the peak amplitude error is full outputs because it's completely lost this initial part of the transient. Now, if you use an infinite processing Sinc filter, then it will perfectly reconstruct the original transient. And it will get this information back. So, how is this done? It's done by the interpolation filter, and it recreates the missing information. And with that particular case, it will recreate the pulse that didn't exist. There's a theory called Whittaker-Shannon sampling theory. And this proves that if you have an infinite tap length F.I.I. filter, you will perfectly reconstruct that signal. It will be no different whatsoever. You could be sampling at 22 microseconds, use a Whittaker-Shannon interpolation filter, it will be exactly the same as if you were sampling at 2 picoseconds. You would get exactly the same waveform. There's only one requirement that you need for this. The signal must be bandwidth limited. So long as it's bandwidth limited and you have a Whittaker-Shannon Sinc Function filter, it will perfectly reconstruct it. So you will get this missing pulse back. So, how is the reconstruction done? You use something called a Sinc function. Now, a Sinc function is just a simple illustration here of the impulse response of a Sinc function. And this thing decays away to 0 in an infinite period of time. So it requires an infinite delay, and it requires an infinite period of time. And if you were to construct such a filter, you would need an infinite amount of processing to do it, which of course is impossible. But this is what theory is telling you, and the theory is a fact. It's not something that somebody's made up, but this is a fact. Now, you've got two issues here. One issue is that the tap length, which defines how effective the filter is, will determine how effective the reconstruction will be. The other thing that you've got is the algorithm that you use to create the coefficients. Now, how the algorithm works is that when you have, let's say you were having a filter that was like this, and you just had a very simple tap length filter, and it was stopping at this point. If this would actually be called a rectangular window function, because you take the perfect sinc function and then you just chop it off. If you then use that as a filter, you get some very bad results. It's pretty awful as a filter. So use something called a windowing function. And the windowing function will taper this out so that it makes it a little bit smoother, and then you get much better performance in the frequency domain. The windowing function that I've used has been optimized, and it's been optimized in a way so that we can reconstruct the timing information to a much better accuracy. And this WTA filter algorithm, which is what I've called it, is something that I've optimized and improved over the last 20 years. And it's been the result of maybe thousands of listening tests to try and fine-tune the performance to get the sound quality right. It's also been based upon the theory and the understanding of how to recover the original timing information properly. I've actually talked over myself. So here we go. Now, I said earlier, a sinc function will mean that you will perfectly recover the original signal. But here you have an impulse going into a sinc function, and here you have something like this coming out. This looks nothing like that. So how can you have a sinc function that perfectly reconstructs the original signal, but this is clearly not perfectly reconstructing the original signal? And everybody says pre-ringing is the evil of audio. Every person will use within this building who designs digital products will say long tap length filters, lots of ringing is bad, and you need the minimum amount of ringing as you can possibly get. Everybody's wrong. The paradox of having a Dirac impulse response and it not reconstructing the Dirac impulse response is because a Dirac impulse response is an illegal signal. It's not bandwidth limited. Now, the Dirac impulse is a very, very powerful way of actually assessing how the filter works, because it's actually telling you what all the coefficients are. And it's extremely useful. But you should never use a Dirac impulse to tell you about the sound quality of filters, because it's an illegal signal. It's not bandwidth limited. A bandwidth limited signal would mean that at fs over 2, 22.05 kilohertz, you have zero output. With a Dirac, you have the same level at 22.05 kilohertz as you do have at DC. And this is the reason why the whole audio business has got the situation completely wrong, because they've forgotten the simple fact that you should not use Dirac functions to tell you how good the sound quality of a filter is, because it's not bandwidth limited. Very dry voice today, right? Another problem about not sleeping is I have a very bad cold as well. So how do we manage to reconstruct? The digital data here is zero, but we actually managed to reconstruct this part of the sine wave. And how does it manage to do that? What actually happens is every single piece of data here creates its own impulse response, and you have the little pre-ringing, and the pre-ringing adds and subtracts with all the other pieces of information. So having the pre-ringing, when you add the pre-ringing together, you end up with that lump here. But there's no pre-ringing further on because it's a bandwidth limited signal. So it's essential to have pre-ringing to reconstruct the transients properly. One thing that I get asked a lot is, what is a tap? So I thought I'd actually mention what a tap actually is. This is a mathematical representation of an F.I.I filter. Don't worry about the maths, it doesn't matter. But what we have the data coming in here, and then we store it in the register, and it gets delayed, and delayed, and delayed. And then there's a coefficient here that is multiplied by the data, so this is actually a multiplier. But the key idea of taps is that the multiplier taps into the delay line, and that's why the term taps has been created, because you're tapping into the data. Now, the way it works is that you have the delays, you have the coefficients, which has been worked out by the filter algorithm that you've chosen. So my coefficients are calculated from the WTA algorithm. They get all added together and accumulated, and then you end up with a new output. It's fairly simple. The algorithm has a huge influence on the performance. When I first started playing around with WTA filters, we're going back to about 1998. At that time, FPGAs were just about capable of doing an F.I.I filter, although I needed 3 of them. It was capable of doing an F.I.I filter. What I found was that a long tap length filter, using a standard Kaiser function, for example, sounded better. And every time you doubled the tap length, it sounded better. And that's exactly what I was expecting. And it sounded better in the ways that I was expecting too. Bass definition was better. And we know that because transients are important for bass perception. Soundstage was sharper. And we know that because that's where the left to right imagery is used. Timbre reproduction was better. And we know that because timbre is determined by transients. But then I thought, hang on, there's no way I'm going to get more than 1,000 taps at that stage. Is there a way that I can change the algorithm to recover the timing information more accurately? And I spent several months worrying about this issue, and there was a few stumbling blocks on the way. But eventually I managed to crack a solution and found something that was very important. And then I adjusted the algorithm, and I found that using this algorithm gave me a 10-fold improvement in sound quality. So that a 256 tap WTA filter sounded better than a 2000 tap Kaiser function filter, which is the standard filter function that people would use. But that didn't mean that we could throw away tap lengths, because when I went from 256 taps with a WTA to 1,000 taps with a WTA, it still sounded a lot better. It sounded a lot better. So the tap lengths are crucial in terms of reconstruction of the transients. As time has gone by, we've had Moore's law kicking in. FPGAs have gotten much more powerful. They're now incredibly powerful. With the DAC 64, I was at 1,000 taps. With the QBD 76, I was 18,000 taps. Hugo, which was a huge project for me, and a huge project for Chord, that was 26,000 taps. And then Dave came out at 164,000 taps. Every time I increased the tap length, the sound quality got better. And it got better in exactly the same ways that I've talked about before. Better bass, better instrument separation and focus, better sound staging, better timbre reproduction. Around 3 years ago, Xilinx launched a new family of FPGAs, which has ended up first in Mojo and now in Hugo 2. The trouble with Xilinx is they launch products, and then about 3 years later or 4 years later, you might actually be able to buy the devices. And for my Davina project, which is an ADD converter, this device was now becoming available. So I decided to use that for Davina. And then we had the issue that we needed to upgrade the blue transport. So all the work that I'd done on Davina, I just ported it over, dropped it in, and this became the new Blue 2. So it uses this new FPGA. It's got 740 DSP cores inside it, 200,000 odd logic cells. That's an enormous amount of gate count and processing. So how many taps can we do with this kind of device? and it came out to be just over 1 million taps. And the Blue 2 is the first product that we've got that's using this million tap length filter. And we've called it, or I called it, the M scaler. Why 1 million taps? This is quite an interesting situation for me personally, because in the 1980s, obviously listening to vinyl, I started to buy digital recordings. I think the first recording I bought was Telarc's 1812, which had enormous wiggles on the vinyl, and it was quite crazy, and I played it loads of times. And I first heard it, I thought, wow, look at that treble, it's so bright and incisive, and wow. And then after a bit I thought, hang on, that treble doesn't actually sound real, it sounds distorted. And then I thought, hang on, this soundstage is a bit flat. It's actually quite mechanical and it's not very nice. Then I realised, of course, that this wonderful new digital recording, which everybody was saying was the future, was sounding pretty awful, and that musically was appallingly bad. So that set me thinking. And I knew about the issue of timing, because when I was studying electronics, I used to go into the psychology department in my spare time and read about physiology of hearing and the importance of timing and transients and all that sort of thing. A few months later, we were doing Whittaker Shannon sampling theory, and they were talking about digital audio is fine because you've got this sampling theory that proves it, and you need a Sinc function and you recover everything perfectly. But we didn't have F.I.I filters, we just had ordinary LC filters. And I realized that immediately you would not be able to recover the transient timing information properly. And this would be a fundamental flaw of the whole system. So I thought, okay, we've got 16-bit CD. What do we need to do in terms of the Sinc function? We'll make the Sinc function 16-bit accurate. And what number of taps does that come out at? And it came out at about 700,000 taps. So you need something like 1 million taps. This was in the days when a microprocessor was about 7 years old, and I'd done in my summer holidays, I designed a computer for an oil rig for the North Sea, and this was a oil flow monitor that used a microprocessor. Had 2K's worth of memory, and we managed to squeeze all of the code in assembly language into 2K's worth, 8 bits. That was state-of-the-art microprocessors. My first experience of computing was using cards, writing on the cards and creating tape out and all that kind of stuff. So, 1 million taps, that was impossible. And that would never ever happen because we didn't even have FPGAs, we didn't have DSPs, we didn't even have PCs. And I thought, this is the fundamental flaw of digital. Digital will never be able to recover from this, and we're in major trouble. So to me, personally, to create a 1 million tap length filter was quite, something I've been planning for and hoping for. As FPGAs got better, it's something I've been planning for a very long time. But what was curious about this was that when I was doing the listening tests for Dave, I initially had the 26,000 filter for Hugo, and I designed the 164,000 tap length filter for Dave. First design didn't work, I couldn't get time enclosure. The second design, which changed it, also didn't work, I couldn't get time enclosure again. Time enclosure is when you design an FPGA, the FPGA tools place and route the design, it then does a check for you to check that everything is going to be okay in terms of timing. Because you've got a 9.6 nanoseconds clock and it takes 13 nanoseconds to compute the result, you're going to get the wrong result. So time enclosure is something that's essential you have to do with FPGA work. It's something essential, all digital systems you have to make sure your time enclosure is correct. So it took 9 months to design this damn filter. And I wasn't doing anything else but designing this F.I.I filter. And I plugged it in and listened to it, and it sounded better. It was just bit better. It wasn't something that was transformational, it was just better. So I thought, that's good, okay. I wasn't expecting a major change with the M scaler. And I wanted my life to be easy, because I had lots of things to do, so I just did 500,000 taps. Because I knew we'd get time enclosure, I knew I'd have no problems with memory, and it would just work first time. Did it, compared it to Dave, and I had probably the biggest shock over the last 5 years in terms of sound quality. Completely unlike anything I'd ever heard before. And I'm still not quite sure the reason why this sudden change from 164,000 taps to 512,000 taps has made such a difference. Part of it is down to the fact that I'd forgotten that in the interim period, I'd improved the WTA filter. I'd also gone from an 8FS filter to a 16FS filter. So things had actually changed differently. And I suspect that's part of the reason for it. Well, then I heard this 512,000 tap length filter. I knew that the FPGA was just about capable of 1 million taps if everything would fit together. If I could get the time enclosure correct, there was just about enough memory to do it. But it was going to be a major challenge. The biggest challenge, actually, I did an initial test where I took the 512 thing and ran it at double the rate, and it met time enclosure, so I was happy about the timing. Biggest problem was the memory, and actually condensing the memory, because when you use memory, it doesn't get used efficiently. So the biggest problem was condensing the memory so it was used efficiently. So I had to come up with a completely new architecture for the way I normally design filters. And this is the architecture. This gives you a flavor for how you go about designing a 1 million tap length filter. You've got, I think it's 132 of these individual modules. And within each individual module is actually 8 DSP cores, 1 data memory for your SRAM, and 1 coefficient memory. And the reason I've got large blocks of memory is that it becomes much more efficient when you're packing the memory together if you do it as one large block, rather than doing lots and lots of small blocks. Normally I would have 1 DSP core with 1 memory block. So doing it this way made the memory much more efficient. There's another benefit in running it this way. It was much easier to code. And that's something, I see you're smiling, that's something that's really crucial when you're doing a big project. The efficiency of coding is very important. This made it was a lot easier to code because I've reduced the coding size by a factor of 8 because it was 8 types of blocks. So, did that, and 500,000 tap, 1 million tap, big change in sound quality. Massive change in sound quality. But there was something strange about it. And it's something that everybody that's heard the M scaler recognizes. The soundstage opens up. And that's the first thing you hear when you plug an M scaler in. The soundstage deepens enormously. That is very, very strange, because every single time I've changed an interpolation filter in terms of tap length and in terms of the WTA coefficients, the depth never changes. Depth is actually about a function of small signal nonlinearity. And small signal nonlinearity can occur within filters, but you can arrange that out by changing your architecture and doing things to the correct level so that you avoid truncation problems and blah, blah, blah. But that's a fixed issue. So it's very strange that depth and soundstage was so much different. I suspect, and this is just a suspicion, the reason why the soundstage opens up is that the time period that the filter is now operating over is 1.4 seconds. That's about the same time period that the RT60 is for an orchestra, so a chamber, an orchestral hall. RT60 is the decay period it takes for reverberation to decay away by minus 60 dB. And of course, reverberance is an important depth cue. So I suspect there's something going on about that that's telling us about depth. But it's a puzzle, and I love puzzles. when you're doing listening tests, I'm often doing listening tests, the most powerful listening test is when nothing happens, when you can't hear any difference. Because that means that you've made the variable so small you can no longer hear the difference. And that's brilliant, because it means that there's no question of interpretation about what you're listening to, because sometimes you can hear something, think it's better, but it's actually worse. When you hear a null event, that's really good. When you hear a situation where it sounds exactly as you expect it to do, that's good, because it means your understanding is perfect, but it's boring, because you've got nothing else to work on. So this is a really quite interesting challenge, and it's something I'm going to be spending a lot of time thinking about. So the future. Oh, I've gone quite fast. Davina A to D converter project. This is something that people who have been reading my blogs will be aware of. This is an A to D converter that is completely different to conventional A to Ds. And it's different for a number of reasons. 3 primary reasons. One is A to Ds have huge amount of aliasing involved in the conversion process. For example, a standard A to D converter will take the output of the analog noise shaper at 1 bit or 5 bits at 3 megahertz, and then use a moving average filter, or what they call a Sinc filter. It's not the same as the Sinc function that we were talking about earlier, and decimate that down to 384 kilohertz or 768 kilohertz. These filters are actually quite crude, and they have attenuation of around 20 dB, and you get lots of aliasing from these filters. The normal answer of the aliasing is, well, the aliasing is occurring at 200 kilohertz. Who cares? No one can hear at 200 kilohertz. The problem with aliasing is that it changes your timing of transients, and that you can hear. And I know this is a fact because I've done different aliasing filters, and you can hear huge changes when you get the aliasing right or wrong. So that's point number 1. Point number 2 with the Davina project is that depth perception is crucial, and one of the things I'll be talking about tomorrow is the depth perception on the noise shapers of Dave, when I found that you need noise shapers to work to 350 dB accuracy to preserve small signals. So when you listen to a noise shaper that's at 330 dBs performance, which is a stupid number and a stupid capability, and go up to 350 dBs performance, which is another stupid number, you can still hear the difference. And yet the change is minute. The noise shapers that's built into the Davina project are 360 dB noise shapers. Standard A to D converters will have noise shapers that can only work at 140 dB. And what I'm hoping with this is that we will get recordings where you can properly perceive depth. So that's another strand. The third strand is noise floor modulation. A to D converters have huge amounts of noise floor modulation, and it's due to the fact, well, it's due to lots and lots of different reasons. Noise floor modulation is crucial in terms of sound quality. And what happens with noise floor modulation is as the signal increases, the noise floor pumps up and down. And you can hear this even at levels at minus 200 dB, so unmeasurable levels, you can still hear the effect. The Davina project will have, I've already tested this aspect of it, 0 noise floor modulation. A standard A to D converter has about 4 or 5 dBs worth of noise floor modulation. And when they make test equipment, for example, the APX 555, they have to use 4 A to D converters and a notch filter, so that one A to D converter is just looking at the residual signal, no big signal, no noise floor modulation. The other A to D converter is just looking at the fundamental, and you don't have to worry about the noise floor modulation because it's not using the noise. So they have to use special tricks to glue these two filters together. We won't need to do that with the Davina project. I'll be able to record at 768 kilohertz, which is what the M scaler is working at. But I'll be able to do some interesting things. We'll be able to check how good the M scaler is. Because I've gone from 500,000 taps to 1 million taps, and it's clearly audible. Does that mean we need to go, and that gives you 16-bit reconstruction performance? Does that imply that we need to be 18-bit or 20-bit or 24-bit? If you want 24-bit Sinc Function reconstruction, you need 256 million taps. And it will take a couple of minutes for the signal to go through your DAC. So that's never going to happen. And I doubt very much that's going to be audible. What I can do with the Davina project is I can take a native 768 kilohertz recording, like I was designing the decimation filters last week before coming here. I can take 768 kilohertz recording, bandwidth limit it to 48 kilohertz, keep it at 768 kilohertz, and then create a new file. So you're now hearing 768 kilohertz, and you're now hearing the effect of the bandwidth limiting. My suspicion is bandwidth limiting is not important, but we will know for certain what the effects of bandwidth limiting is. And you can have different ways of doing bandwidth limiting. You can do it with pre-ringing, linear phase, or minimum phase, with no pre-ringing. And perhaps this might be a situation where pre-ringing is actually important. So we could experiment and try different bandwidth limited filters. I can also then take this bandwidth limited signal, decimate it, convert it to 48 kilohertz, put it into the M scaler, create it to a 768 kilohertz file. And then we'll be able to hear the difference between the bandwidth limited signal and the reconstructed signal, and see how much of a difference in sound quality we're going to get. Then I'll know for certain how much of a problem we really have. And certainty is an issue that is the holy grail for audio. Because when you're designing, you're often designing in the dark, in terms of you don't know how far to go. This will completely tell me how far I need to go. So I'm quite excited about this. And also, perhaps I'll be able to find out why this depth information suddenly got so much better with sound staging. So, now's the time to ask some questions, and we've got plenty of time, so, yes?
You guys want to yes. I mean, you could yell.
So, my name's Jeremy from Seattle.
Hi, Jeremy.
Nice to meet you. Great talk, fascinating. A bit above my pay grade, but I'm really enjoying all the theory. I was curious. I'm a computer guy by trade, and graphics is something that I see a ton of development in. And I'm wondering, have you considered the usage of some of the modern GPUs for parallel processing and programmability, and what pros cons?
You're a graphics designer.
No, but
Yeah.
I'm a gamer.
Yeah. I'm an FPGA guy. So I'm getting a bit old. So you have to work with the tools that you've got. And secondly, we want to make devices that work in audible. You know, my goal in 10 years' time is to have an M scaler that will fit in your pocket. And you will only ever be able to do that with an FPGA. So going down the GNU route is a bit complicated, and it means dedicated users. It's not a product you can go into a shop and just buy. So it would be something of interest to Cord. But even if it was, it wouldn't be something that I'd have the capability of working on. So each to their own. Okay.
Do you think you'll be able to get this all in one chip eventually?
Well, that's it. That one chip. It's about 1 centimeter square.
You mean that's all the M scaler?
That's the whole M scaler.
It's-
Absolutely. Yeah, it consumes 12 amps of current on the core, but the core is at 12 amps.
You have to cut that down if you're going to put it inside of your pocket.
Exactly, exactly. It's actually only 12 watts because the core voltage is 1 volt. So it's not quite a scale, but there's no way you can have 12 watts in your pocket. That's not going to happen. But you know, when you imagine you've got 740 DSP cores, and each DSP core can do 1 F.I.I tap. If you use per clock cycle, so if you use a microprocessor, you need to pull out from memory the coefficient, pull out from memory the data, put it into a multiplier, store the result, put it into another memory, store the result, put it into an accumulator. So there's lots of processor functions that need to happen. With an FPGA, you can do everything in parallel. And the DSP cores, it just gets pipelined. So 1 clock cycle, 1 tap. So the FPGA is a very, very efficient way of processing this kind of stuff. So 740 DSP cores, that's a lot of power. Yes?
When you analyze, testing, okay. When you analyze the sound quality of your products, like when you increase the tap length filter and you hear an increase in sound quality, do you quantify that difference in sound quality, or is it all based on listening tests?
Oh, listening tests is a major headache.
Yeah.
And it's a headache for a number of different reasons. You have to be completely neutral. You can't approach, your emotions must be completely flat. And often, when you're excited about listening to something you've spent 9 months working on, that can skew your results. And when I was young, 15-year-old still mucking around with hi-fi, I built my own hi-fi and I used to play around and experiment and do things. And what I used to do was to do listening tests to see whether such and such made a difference. And I told myself that I had made a massive improvement to the sound. Convinced myself and then played a record and it sounded much better. So the way you approach the listening test is crucial. The other problem is that when you hear something as an improvement, is that a real improvement because it happens to suit your system? So for example, let's say your system is too dull and you have some noise floor modulation to make it a bit brighter. It makes the balance better, but actually you're making it worse. And sometimes it is almost impossible, or actually impossible to tell the difference between a little bit of noise floor modulation, making it sound brighter, or a fundamental improvement in transparency, making it sound brighter, because when the detail resolutions are better, you can hear better. So you have to be hyper careful about your listening tests. Now, part of the benefit that I've got is my listening tests are specific. So I'll be listening to 1 tap length filter, everything else being the same, another tap length filter, everything else being the same. And it's quite easy to hear small differences. But you've got to be really, really careful. And listening tests are not an easy thing.
Where do you want to go?
Fascinating talk.
Thank you.
You've just sort of acknowledged the many pitfalls of listening tests, but the great importance of listening tests, and also how your own emotions might color
Yes.
your interpretations. And so it occurs to me, and so I guess the first question would be, are you the only person who is doing the listening tests when you are developing products?
Yes,
Okay,
because it's there's too many listening tests,
right.
and there's just so many of them.
Just logistically, it's
It
difficult.
yeah, and I don't, I'm designing for me. I'm not designing for you guys
Yeah,
or Chord. I'm designing for me.
okay.
That's always been the nature of what I do. Now, if 100 people love what I do, that's great. If 100,000 people love what I do, that's also great. Bit more money in the bank, but that's not the primary motivation. It's doing what needs to be the best,
Right.
and only I can answer that question.
Okay.
So, but having said that, once the product is finished, then of course other people will listen to it. But I've been doing this for many, many years. Chord just leave me to get on and do it, and they know it's going to be better, and there's an awful lot of measurements that gets involved as well. So the measurements have to be right, and I'm a bit pathological about measurements, because with measurements you have certainty. And also everything I found with measurements is that when you improve the measurements and everything else being similar or the same, you get better sound quality. So that's one of the reasons why the measurements of my products are so good. It's because I know it's very, very important. Some designers use distortion as a way of changing the sound, and I'm opposed to that. I don't like that concept. My idea is that you hear what you're hearing on the original recording. And the real strength of the Davina Project is that I'll be able to make my own recordings, and I'll go from microphone to loudspeaker, and I have complete control over the whole process. And that power I've never had before, because you can never be certain. And this will supply a lot more certainty to what I'm actually doing. But any listening test is backed up by theory. So when I'm doing a listening test, I need to understand why something sounds different. That's why this interest about it sounding so different on the sound staging, why that's so fascinating, because I don't understand it, and I need to find out why, because maybe there's another trick that I'll discover, and we'll get better sound quality later on.
Is there any point where you think it makes sense to open up listening tests to other people? Like when you have a prototype of an actual product, does it make sense at that point to have other people listen?
The only time I get other people to listen is when something so enormous has happened, or something that has extraordinary consequences. So, for example, in the 1980s, I was listening to mains cables and trying solid core mains cables against stranded mains cables. And I was using a preamp that had 3 stages of regulation. It had 220 dBs worth of power supply rejection. No way that should make any difference to the sound. And I thought, I'm crazy. So I got I am crazy. But I got my girlfriend to do a blind listening test with her. It wasn't double blind, it was blind. And I said, listen to this, listen to that, listen to this, listen to that. What do you think? She said, oh, that one sounds smoother. She'd been involved in this before, she knew the handles that we use. That one sounds smoother, warmer. And that was exactly what I was experiencing. So the 350 dB, 330 dB thing for depth. Now, that is just a crazy number. What you're basically saying is that if there is the smallest possible error the brain can detect, and that's just an impossible concept to get your head around. And at the time when I discovered this, I thought, I can't post about this, because people will say you're an idiot. 350 dB against 330 dB, you're an idiot. That's impossible to determine that. But I could hear it, and I got other people to listen to it, and they could hear it. One of the really interesting things I had with my silicon design career was that they spent millions of dollars acquiring IP that I patented. And my 3-year contract was to embed that IP into the company so they could run off and do their own thing without me being around. And so I had to go through all the coding and go through the design and go through every aspect of the IP so that they fully understand it. The engineers were very, very bright people, brighter than myself. But they refused to accept, they kept arguing with me, this can't make a difference to the sound. You're talking rubbish. And then we had these arguments. I said, no, you've got to do it this way because you've got to do it. After about 2 years of this, I got fed up. So what I did was I did an experiment, and I had an FPGA with a noise shaper. The first noise shaper was 180 dB performance. The second was 200 dB performance. And I got one of their engineers who wasn't an audiophile down into my home. And I said, listen to this, listen to that. 180 dB noise shaper sounded harder and brighter because it had some noise source modulation inside it. Detail resolution and the depth of the 200 dB was much better. And this I knew, of course. And he held it. And he said to me afterwards, he said, what I'm surprised about is not that I can hear the difference from this 180 dB to 200 dB. What's really surprising me was how easy it was to hear the difference. So he then filed a report, and then after that I got no crap from the company about doing it.
Nothing like real experience to change minds.
Yeah, and exactly.
I'm here, Matt Jitterburn from Audio Sounds Review. I have a simple question. I'm confused about your pipeline delay.
Okay.
If you have 1 million taps and playing 44.1, you said you had only 1.5 second latency.
It's actually 0.63 seconds,
Yeah.
but it's looking at 1.4 seconds worth of data or 0.7 seconds worth of latency. So, because
you have 44.1K worth of samples, how'd you get 1 million taps out of that? Or are you running it at oversample?
it's oversampled at 16
that's why
FS.
you're counting it.
Yeah. So when it's running at 44.1, it's about 0.7 seconds worth of latency.
Right.
So when you stop recording, it takes 0.7 to come out, and it's analyzing 1.4 seconds worth of data. So for Blu-ray, for example, at 48 kilohertz, it's 0.63 seconds and 1.2 whatever, 0.63 times 2 is. The surprising thing is Blu-rays, what I do is I rip Blu-rays to my laptop, use JRiver, and set a negative delay on the JRiver, and I can run the audio in perfect sync, and it just sounds stunning. It absolutely sounds stunning.
Yeah, just an observation on the transient perceptibility of that. In lossy audio compression, like MP3, AAC, and so forth,
Yes.
frames of audio is taken and transients, so then when you quantize them in frequency domain, they wind up smearing pre-echo.
Yep.
At about 320 kilobits per second or so, 99% of people no longer can hear that pre-echo, and it's massively above the rates we're talking about.
Yep.
And I've done tons
Well,
of
when I hear AAC
yeah.
Against regular 16-bit, AAC sounds soft by comparison, and I can easily hear it using a WTA tap-link filter. What happens when you get timing uncertainty on the transients? What happens is that the brain can't perceive the starting and stopping of notes, and when it can't perceive the starting and stopping of notes, things sound soft because you can't hear it. It blurs it. With AAC, you get a softening effect, and it's very, very easy to hear AAC from that. And it's simply because the timing of transients is being encoded to a poorer accuracy than one would expect. The same thing occurs with DSD, because DSD, and we're talking about this a little bit more tomorrow, DSD has its own timing errors. They're not the same timing errors that we've got here, but they're amplitude related. So in the case of DSD, the amplitude of a transient will change the time delay as it goes through the noise shaper. So a big amplitude transient gets through the noise shaper very rapidly. A small amplitude transient has a long time delay because it takes time for the integrators to recognize the error and for the error to come out. And what you hear with DSD is things sound soft, and again, it's because of the timing inaccuracy of transients.
I guess my comment is that in control testing, when it's fully blind, double blind, people cannot pass that test when it's orders of magnitude more than what you're talking about.
Yeah.
So I hope we don't have a disagreement there, because I've tested many audiophiles, and they fail, predominantly hearing much higher amplitude errors here.
Sure.
Now, you can train your ears. I'm trained, so I can hear the higher, lower thresholds than others.
I have big problems with double blind testing.
Okay, all right.
Because the minute you start creating confusion in terms of which you're actually listening to, then people get stressed, and then your sensitivity just falls apart. So, yeah.
Okay. I'll just say that if you're trained, that doesn't impact you. So I pass the double blind test, when other people can't, because I am trained. I can hear.
Sure.
Appreciate it.
Thank you.
Time.
Time, okay. So, thank you very much.